we said we'd talk about some periodic table, right? I mean, we did mention atomic radius at the end of the last section. Now, this is a measurement of the size of an atom. Usually it's expressed in picometers, like 10 to the negative 12ths of a meter. This is a thousandth of a nanometer. Or just something times 10 to the negative 12th or similar meters. The distance from the center of the atom to the outermost electrons. Now, since the electrons are in an electron cloud, so to speak, this label, how do we calculate this actually? Well, for diatomic molecules, like say H2, we take the nuclei and we find the distance between them and we divide that by half. What if we have a metal, in which case it's a bunch of nuclei in a electron C? Well, technically nuclei and all but the valence electrons stay in place and the valence electrons float around. So how do we measure this? Well, we measure the density of the metal, we compare it to the atomic mass, and thus we get how far these are spaced apart. And if we know how far apart they are, and what this crystal structure of the metal is, if it's this type, it's a certain formula. If it's another type, it's another formula. So the point is, you find out how far this is, and so on, and you divide that by half to get the atomic radius. Now, what is the effective nuclear charge? Well, this is the force experienced by an electron in an atom due to the positively charged nucleus. So let's think. Why might it be that the more electrons and protons we add, the smaller the atoms? Okay, so here we have more protons pulling on the same outer shell. So instead of just adding a whole new shell, like going from neon to sodium, we keep on adding more electrons to the same shell. Okay, sure, that crowds a little bit, but then the effective nuclear charge grows fast enough that it crunches down really fast. It's like here, oh, the outer shell is 1 electron, sure. So they don't crowd each other at all. But in the center, there is only 1, 2, 3 protons pulling it in. Whereas here, yes, the outermost shell has 7 electrons, but there are how many electrons pulling it in? Well, 9, right? So here you end up with many more protons to electrons. And why is it the case that here you don't see the radius changing very much? It's because proportionally speaking, the increase in the effective nuclear charge is not as big. Because this is far enough away, and because there are already enough protons there, that increasing it a little bit further wouldn't be too drastic, not like 3 to 9. Well, what else can we see from this diagram? Do you think it's going to be easier to take away an electron that's held really close to the nucleus, or one that's circling far away from the nucleus? Well, circling is not quite the right term because they don't actually circle, but conceptually it should be pretty obvious that the one that's closer to the positive nucleus is going to take more energy to remove. So, plus ionization energy. Now, ionization energy is also, well, we specifically mean first ionization here. Now, this is also a gauge of something else. It's a gauge of electron affinity. And what about here? Is it going to be easier to take away one that's really far away from the nucleus, or one that has less protons in the nucleus but is really close? Well, plus ionization energy. Energy. This is also part of why we mentioned, to quote our mentor at the Canadian Chemistry Olympiad training camp, if somebody drops cesium in water, run. Why? Because it takes very little energy for cesium to lose that outermost electron, whereas hydrogen actually takes a considerable bit, and lithium takes quite a bit too. What does that mean? That means cesium gets reacting very fast. We will learn why this is the case later on when we talk about reaction rates. Now, ionic radius. Why do you think that cations are generally smaller and anions are generally bigger? Okay, so here we removed an entire electron orbital, basically. So it's completely understandable that the cation should be much smaller than the original atom. But wait a second. Here we didn't add a whole orbital, but this chloride ion is so much bigger than the chlorine atom. Well, that's because the electrons crowd each other, and also because of another reason. Because when we're measuring the chloride ion, we're measuring it with another atom that has lost something. So this may actually be a little bit bigger than it quite should be. And another important thing. When they measure the chlorine atom's radius, it looks something like this. So they're measuring this distance here. Do you see something wrong with calling this the atomic radius? It's different from over there, right? With sodium, it's a metal. It doesn't have this sort of concern to deal with. So, this is a slightly biased example, but it is also pretty typical of the sort of numbers you're going to end up getting. No, anions don't just double in size, but, well, they do increase. Why? Because of more electrons crowding. And cations, even if they don't lose a whole orbital, they have less electrons crowding on the outside, and therefore the effective nuclear charge, because electrons getting between each other in the nucleus reduces the effective nuclear charge. So, not having so many electrons to get in the way of each other means the nucleus might as well be more positive. Well, technically I should have said it is effectively more positive. Oh, look, here's ionization energy and electron affinity. Do you see a pattern here? Here's the first period, so hydrogen is not that low. Helium is really high, and then it keeps on climbing across each period. And the larger the period number, the lower the energy. Well, what did we say up here? Oh, look. This corner has the highest ionization energies, and this one's the lowest. So what is ionization energy? Well, other than the fact that we know it's a gauge of electron affinity. Well, if you have an atom in a gaseous state, or an ion for that matter, if you're going to take away another electron, or take away one electron, if it's the first ionization, then that's the energy required. Now here it says kilojoules per mole. What's a mole? Well, it's 6.22 times 10 to the 24th. 23rd, I think. So it's a very large number of atoms. 1 mole of carbon-12 is 12 grams. That's how the mole was defined. Now, electron affinity. The energy change that occurs when an electron is added to a neutral atom in the gaseous state. Well, this you are not going to be working with all that often. Eventually, you'll just use a measure called electronegativity. But for now, okay, electron affinity is how much energy is needed or is released when you add an electron to a neutral atom while it's a gas. Sure, let's go with that. Okay, in summary, atomic radius, ionic radius, ionization energy, and electron affinity are all atomic properties that exhibit periodic trends. What does this mean? If you look on the periodic table, each group is generally somewhat similar, and they display a similar trend as you go down a group, compared to usually other groups. Now, is it completely consistent? Basically, yes. I mean, there are a few minor bumps, but those are few and far in between. Much as the fact that when Mendeleev first organized the periodic table, he did it by atomic weight. It was only later that he realized that he had to flip a couple of them around because their most common isotopes were different in weight than you would expect, so that it's organized by atomic number. So the trends for atomic radius can be explained using the idea of effective nuclear charge, which means how effective the nucleus is at holding in the electrons. Now, this is a good diagram. Atomic radii increase towards this end, and atomic radii decrease towards that end, where electrons are held tighter. Well, since the atomic radius is the distance from the center of the nucleus to the outermost edge of the electron cloud, and the nucleus is like an ant in a stadium if the atom is a stadium, then it's perfectly reasonable to say that, oh, holding the electrons tighter means not only your first ionization energy goes up, but also your radius goes down, because the volume of the nucleus is negligible in an atom. Now, remember this diagram and remember it well, because we'll be using the concepts here a lot. Notice that the halogen column is completely whited out here. Why? Because did you see how obscenely huge the ionization energies are for the halogens? Okay. Did you see how the noble gases column here is completely whited out? Well, we saw earlier how obscenely huge the noble gases ionization energy are. I mean, they didn't put radon down as a red dot because it wasn't as obvious, but it's still pretty clear that it's much higher than for the rest of that period. Now, once you get this down, that is it for this section. Except for the fact that cations are smaller and anions are bigger, but those are kind of just common sense once you think about it a little bit. Well, hopefully it will be, because if it's common sense, that's good. Now, once you have made all this stuff from this first chapter common sense to you, you'll be ready to get started on some more serious chemistry.